Good morning, everyone. All right. You ready to get down to business? We were talking last time about exponential functions. And let's see, let's look real quick on our calendar to see where we are here. We're supposed to have a test. Let's see. It'd be next, I believe that's going to be next week. So next Thursday, we'll have a third exam. And I'll send you out a review for this exam, hopefully in the next 24 hours. That way you'll have it for the weekend and you can start preparing for it. So when you look at the review, you'll have a good idea of what to expect, what topics will be covered. Let's see, what else do we have? Yeah. So our last exam, exam 2, covered up through graphing of parabolas. So our next exam will start with the graphing of the polynomials, then the graphing of the rational functions, and then exponential functions. Don't think we'll get to logarithmic functions yet. So everything we cover today will be on the test, but what we cover next week on Tuesday will not be on the test. Any questions on that? Okay, so last time what we discussed, we did a couple of examples where I showed you where exponential functions kind of come from, but let's get down to the actual, algebra of them and how we're going to sketch them. So in general, an exponential function of base A looks like this, a to the x, where we said a could not be equal to 1, and we said that a had to be a positive number. So let's take a look. I'm going to use my computer to graph these, even though we have already done this. I want us to see what happens if we change that a, the base, that number on the bottom. So I'm going to have this graph y equals a raised to the x power. And I'm going to be able to control the value of a. All right. So right now a is 1. And remember, we said a can't be 1. So let me let a be, I'll just let it do that. Okay. So let me move a to 2. Okay. So that was the example I gave you. The very first example where we were folding the piece of paper and looking at the number of squares we got. What we were looking at was, if you folded it once or twice or 3 times, but in general, the function 2 to the x, that's what we're looking at here. This is 2 to the x. This is what its graph looks like, okay? So notice that on the right-hand side, if we go out to the right, it goes up, right? Kind of like a parabola, but it goes up very, very quickly. And then as we come to the left, it doesn't go up, it flattens out. And we've seen this before in rational functions. We saw these things, we call them horizontal asymptotes. They were like little magnets that pulled your function down. If we zoom in on this, you'll see that there's a little gap between the function and the x-axis. No matter how far you go down, we're going to have a little space in there. So it's approaching 0. The graph is approaching the x-axis, but it never gets there. So that's what 2 to the x looks like. Let's look what happens if I make this number bigger. Just watch what the graph does. It just seems like it's getting steeper and steeper, right? Like it's just growing, it's growing faster and faster and faster. So the bigger this number is, the faster it grows as you go out to the right. The smaller it gets, the less steep it gets. Now, what happens if I make this number, well, I can't make it negative. Remember, we said it had to be bigger than 0. But what if I make it a fraction, like 0.5? So let's see, if I move this to 0.5, look what happens to the graph. It almost kind of like, well, it kind of flips over, doesn't it? And now as you go to the left, it grows, right? It's going up and up and up. And as you go to the right, it starts to go down. All right. And if I get closer to 0, hold on, I can't get to 0. So I want to make sure I don't do that. 0.001. Okay, I want to make sure I don't get close to 0 there. So again, the closer I get to 0 as my base, the steeper it gets on the left side. And on the right side still does the same thing. So generally speaking, there's 2 to the x. There's 0.5 to the x. Let me hide this one. Generally speaking, when you're talking about exponential functions, you're going to have one of these 2 shapes. It's kind of like with parabolas, we had either up or down. With exponential functions, you're either going to have the green one or this like purple one. All right. So I'm going to copy this, take this to our notes, and I want to tell you like on the notes exactly when this happens. So when we are looking at these graphs, come on. Okay, so when we're looking at these graphs of f of x equals a to the x, you're going to get this scenario. Okay, this graph goes up, keeps going, right? You're going to get this scenario where it looks like one of these if the a is bigger than 1. So if the base, the number on the bottom is like a 2 or a 3 or a 4, we should get something like this. And the graph, of course, on the left side flattens out and there's like a horizontal asymptote there. So this graph is actually called something. It's called exponential growth. Because as you move from left to right, the graph grows, right? And it grows very rapidly because it's exponential. We talked about that last time, how fast these graphs grow. So we call it exponential growth. Now, the other one that goes up on the left and as you go to the right, flattens out to a horizontal asymptote this way. This happens if the a that you have is smaller than 1, but remember, you always have to be greater than 0 because that's a condition for all exponential functions. You can't have a negative number. What happens if it is negative? Why do we throw this out? You don't want to go look at a graph of something with a negative and see what it looks like, just to see why we look at them. So what about y equals, let me try -2 raised to the x. Where's the graph?
So is it saying like the graph doesn't exist then?
Yeah, this is really weird. We don't appear to have a graph anywhere, right? Now look, it did give us 1 point on the graph. Here it is. It gave us 0, 1. So if we plug in 0, we get 1. Now what should happen if we plug in 2? What would -2 squared be? -2 times -2. Should be 4, right? I'm not sure why the computer's not graphing 4. I'm not sure why. The problem that you get into is the numbers between, like if you try and plug in a fraction into this, raising a negative number to a fractional power is a very complex, it's a very complicated thing, all right? Because you get imaginary numbers in there. And I'm sure you've heard you can't take the square root of a negative number. This is kind of like this is why we can't mess with negative bases. I am a little bit surprised that it's not trying to graph it though. Let me try and, yeah, this is not. Yeah, see, if I define it as a function, see, it's weird. If I define f of x to be this and then ask it to plug in 2, it plugs in 2 and it tells me the answer is 4. But it didn't graph it, which is really strange. But if I try and plug in f of, let's say, 1/2, it says it's undefined. See, and that's true because this really means like the square root of a negative number. You can't do it. So it's weird. Let me try some different software because there is there is a graph. I mean, let me try this. F of x equals -2 raised to the x. And let me ask it to graph this. Yeah, no, ignore that. That's not the graph. I see what they're doing there. Yeah, see it, this. Yeah, this is not, it can't do it either. It's having trouble. So that's why we have to make sure that when we're talking about exponential functions, our bases are positive numbers, because as soon as you go negative, things get weird. All right. So, okay, back to this. If we have a number as our base between 0 and 1, then we should expect this, which we call not exponential growth, we call this exponential decay. Okay, exponential decay. All right, any questions? Just the general idea here. So how are we going to sketch one of these? If I give you an exponential function, how are you going to sketch it? I mean, we have steps to graph a parabola. We have a bunch of steps to graph a polynomial. We have a bunch of steps to graph a rational function, a bunch of steps. But how about an exponential function? Well, I've got good news. It's very easy to do. You just need a calculator, okay? As long as you got your calculator handy, we should be able to do this. So here's your first example. I want us to sketch f of x equals, let's go with 2.4 to the x. So first thing I'm going to ask you, is this going to be exponential growth or exponential decay?
Growth.
Growth. It's growth, because the number in here, 2.4, is positive. Sorry, not positive. It's always positive. Is bigger than 1, right? So we should expect to see growth. So the way we're going to do it is we're actually going to go back to like old school way. We're just going to make a t-table. And we're just going to plug some values into this and figure out points that live on the graph. And we're going to plot those points and just draw it. So we're going to pick some values for x, and we're going to see what happens when we take 2.4 and raise it to that x value. Now, what values we plug in for x are totally up to us, all right? So what I'd like for us to do is let's all use the same numbers. Anytime we're doing an exponential function, let's just all agree to use these same numbers. And here's what we're going to do. We're all going to plug in 0, 1, -1, 2, -2, 3, -3. That's it. Those 7 numbers. That's all I want. So as long as we all do that, we should get the same picture. So let's get on our calculators and let's make sure we can do 2.4 raised to the -3 power. And we talked about how to do this last time using that caret key. The way that I would type this in is I would type 2.4. I'd use my caret key. And then, very important, you're going to put in -3. So on these calculators, your negative key, I know it's hard to see this, your negative key is not the minus key. Your negative key is this key down here underneath the 3. Do not use the minus key. So try this on your own. If you have a different calculator, it's okay as long as you can get the same answer that we get. I'm getting, does anyone do it yet?
Yes.
Yeah.
0.072.
72, yeah. And what we'll do is we'll only go like, let's just say we'll go 3 decimal places. All right. We don't have to go and do everything that's on the calculator. That's a very small number, right? 0.072. That's small. All right. Try the next one. 2.4, raise that to the -2. You should get 0.17. That's a little bigger, isn't it? It's still small, but it's bigger than this number. And then do 2.4 raised to the -1. You should get 0.42, I'll say. That's even bigger. What about 0? What should we all get when we plug 0 into any exponential function?
1.
Right, exactly. So we're going to get 1. That's why when you look at these graphs, do y'all see that on both these graphs? Do y'all see that this point lives on both of them? That's the point 0, 1. Because for both exponential functions, no matter what the base is, when you plug 0 into the exponent, you should get 1, which is why they both go through there. Okay, now plug in 1. When you plug in 1, you should just get 2.4. So it's getting bigger. 2.4, raise it to the second power, you should get 5.76. And 2.4 raised to the third power, you should get 13.824 or something like that. Okay, understand? Anyone have any questions on their calculator for this? Now remember that each of these represent points, right? This is like plug in -3 for X, it spits out 0.072. So I'm going to want to plot that point. This one, I plug in -2, it spits out 0.17. Here I plug in -1, I get 0.42. You get the idea, right? We're going to have 7 points that we have to graph on a graph, right? Put it onto a graph. So when I'm drawing this graph, what I want to consider is this. First of all, the x-axis, I'm going to be at 0, right? Let me go ahead and draw my y-axis now. I'm going to go out 1, 2, I'm only going to go 3 to the left. I'm sorry, 3 to the right and 3 to the left. That's because we all agreed that that's what we're going to do, right? Now, what about the up and down? So what I suggest you do is look at these values, okay? You're going to have a very, very small value that's positive, right? And then the biggest value we get is 13.82. So I need to make sure that my y-axis goes up high enough to 13.82. So I don't want to start doing this because I'll be way off my graph. I'll go 1, if I do that 2, right? I'll go way up there. I don't necessarily want that. So what I'm going to do is I think I will count by 2s instead. So 2, 4, 6, 8, 10, 12, 14. That should be able to fit the graph because the biggest number I get is 13.82. And now it's just a matter of plotting the points, right? Plotting the points. So, you know, start wherever you want. I'll start with the point that we know is on all exponential functions, 0, 1. Let me go ahead and plot that. So 0, 1 would be about here. And look, everyone, we're just kind of eyeballing this. It does not have to be perfect, all right? 0, 1 is there. 1, 2.4, I'm going to do that one next. 1, 2.4. So if I go to the right, I'm going to go up 2.4, I don't know, somewhere around here. Got that one. If I go out 2, I go almost up to 6. 5.76, something like that. And then if I go to 3, I'm almost up at 14. So I'm like right here. And so what I can do is I can connect these with a curve like this and a little arrow at the end, and that will show my exponential growth. Now, as I go to the left, I could use these points, right, and plug them in. But because this is exponential growth, we know that the left side is going to flatten out towards the x-axis, right? So I'm just going to draw a horizontal asymptote dotted line over here. And then all I'm going to do is just make this thing get closer to it and draw a little arrow, and I'm done. Okay, that's what I want. I don't care about you plotting these points. It's going to be really hard. Like, how are you going to plot, you know, 0.072? That's going to be really difficult to do. So, you know, as long as you show that it's just getting smaller and smaller on this side, I'm happy. So what do y'all think? This better than rational functions and polynomials, right? It's just plug in numbers into your calculator. That's it. All right, let's do another one. Let's do f of x equals 0.35 to the x. Sketch this. So what should we expect to see here? Growth or decay?
Okay.
Decay, because the number 0.35 is smaller than 1, right? Okay, so why don't you take a moment to fill out the table. Make sure you can do this properly. Remember, you're going to use -3, -2, -1, 0, 1, 2, and 3 on this table. And I'll give you like 2 minutes to fill that out on your own. And then we'll come back and fill it in and draw a picture. I'll be right back. So I filled out the table with what I got on my calculator. Did anyone have any issues getting those numbers? Okay, so when I go to draw this, I can actually not care too much about drawing anything. My graph doesn't really need to go down because I know it's an exponential function. It should be up here. It's going to be decay, so it should start, up on the left and come down. I'm going to mark out 1, 2, 3 on the x, -1, 2, 3 on the x on the other side. And then how high does my graph need to go? How high should I make this axis?
So 3.
Like 24?
3 left and right. I'm sorry, did you say 3 or 23? I'm sorry.
I said, I'm gonna say 23, sorry.
Okay.
Or 23.32, so maybe 24?
24, 25, something like that, right? I mean, we just want it to be close, right? So you want to maybe count by fives? I don't know, you can count by whatever you want, really, it doesn't matter. I'm gonna count by five, so I'm gonna do it this way. I'm gonna say 5, 10, 15, 20, 25. If you wanted to, you could have said, 5, 10, 15, 20, 25. It doesn't matter, okay? As long as your axis is labeled so I can tell what you're counting by, we're good. So this first point, -3, 23.32, that's to the left, go up, no, right, to the left 3, go up 23. So I don't know, somewhere around in here somewhere. At -2, I'm at 8.16, so 8.16 somewhere around here. At -1, I'm at almost 3, so I'm going to say about right here. And at 0, I'm at 1, so 1 is going to be somewhere around there. And then I'm going to connect those together with a curve. It's going to go up. And then on the right-hand side, I know I have that horizontal asymptote. And so the graph is going to decay down and get closer and closer. That's it, okay? That's all I want. Any questions?
So the X on the left side of the table, the X, all those numbers are on the Y axis, correct?
Yeah, this right here represents a point, -3, 23.32. This is the X value and this is the Y value. So this
Okay.
point, that corresponds to that point right there. The X is -3, the Y is 23.32.
Oh, okay, I got it.
Good? Okay. Any other questions? Okay, so graphing these is not that big of a deal. Would you agree? I mean, compared to the things we have done, this is just calculator stuff. And then a little bit of thinking to draw your graph. All right, so we move on. So the next thing I need to talk about is two very special exponential functions. So when you think about it, an exponential function, right, can have any number as its base, right, as long as it's positive and it's not 1. So there's an infinite number of numbers that you could use, right? You could use 2 or 3 or 4 or 5 and any of those, right? And you go forever. So there's an infinite number of these, but there's two that are really special that we use almost exclusively in all branches of science. And the two very special ones are these two. Okay, the first one is the function f of x equals 10 to the x. So do you see here the base, the number on the bottom is 10, right? That's a very special one. This is called the, hold on, the base 10 exponential function. Because the base is 10, that's obvious, right? And then the other one is really weird, okay? It's this function here. It's the function f of x equals e to the x. Now, I said that the base here has to be a positive number, right? And not 1. And then I just put a letter there. I mean, here 10 is 10. We all know 10 is a number. Here I put e to the x. So you should be sitting there going, well, what's e, right? I mean, because 10 is 10, but what's E? Well, you have to know what E is to understand what's going on here. E is a number. And to tell you about this number, I'm going to try and remind you of a number that you are familiar with that we kind of treat the same way. Everyone here has heard of the number pi, right? Pi is a number. And pi is usually used, it has to do with circles, right? Normally when you see pi for the first time, it's in a circle. Pi, does anyone know approximately what pi is?
3.14.
1.14.
Yeah, about 3.14. See, a lot of you knew kind of what pi was. So most of you are comfortable with the idea that we have this number, 3.14, that instead of writing 3.14, we write pi instead, right? The reason why we write pi instead of 3.14 is because this actually keeps going. It's 3.1415, and it keeps going forever. And it never has a pattern to it. So like there's some numbers, if you think about like let me do 1/3. 1/3 is a decimal is 0.333333, and it keeps going forever, right? So when we want to write this 1/3 as a decimal, we just write 0.3 with a bar on top, and it just tells us it keeps going, right? Here, this number pi, it keeps going with no pattern to it at all. And when you have a number like that, this number is called an irrational number. It's a non-repeating, non-terminating decimal. I'll say it again. It's a non-repeating, so it never repeats, and it never terminates, non-terminating decimal. That's an irrational number. This is called a rational number. All rational numbers either stop or they repeat themselves. I'll give you another example of a rational number. 1/4. 1/4 is 0.25, and it stops. Well, there's an infinite number of zeros, but that's repeating, right? 0, 0, 0, 0, 0. So these two are both rational numbers because the decimals either stop or they continue with a pattern. Any number whose decimal doesn't stop and doesn't repeat is called irrational. And since you can't write them easily because they never stop, never have a pattern, then we usually give them a letter or something to symbolize what that number is. If it's an important number, it could be not important, but pi is very important. So we call this number, we use a symbol to represent it. We use this Greek letter, right? Pi. Pi is Greek. It's basically the letter P. All right. Now, E is an irrational number. It's just a number, though. At the end of the day, it's just a number. All right. But it's irrational, meaning it never stops, never has a pattern. Now, it's approximately, it's not pi, so it's not 3.14. It's about 2.718 approximately. Now, of course, that keeps going, right? So I can't tell you what the rest of it is. Let me show you something. This is let me see what happens if I do pi 100 digits. Let's see if this computer can do this. There we go. So this is, I know it's probably very hard to see. I'll try and make it a little bigger here.
There are lots of songs that teach you the 100 digits of pi.
Yeah, there's ways to memorize this pattern. Well, there's no pattern, okay?
It's just memorizing numbers.
You're just memorizing numbers. So if you look at this and look through here, it's very random how this happens, okay? And you cannot predict what the next one's gonna be. There's no pattern to it. Do y'all understand what I'm saying? So back in the day, before calculators, people that were studying math would have to memorize pi. And so they would have competitions to see like who could memorize pi the furthest. And it was like this status symbol that you could carry around, like, yeah, I know pi out 50 digits, you know? And I actually work with a guy who's in the math department, who is an older professor. He's in his 70s. So he grew up in that generation without calculators. And he, at some point, knew pi out 120 digits. And to this day, he still knows it at least 60 digits. So me personally, I know like the first 5 and I don't care after that. I really just don't care because, you know, if I need 100 digits, I can go get it. The world record, okay, for the person who knows pi out the furthest correctly. Oh, are y'all okay? Uh-oh, something happened. Am I still here?
You're
For you?
still here.
You're still here.
It said that I signed out. Weird. Okay, I'm still here. So the world record is someone who memorizes out, and I don't want to give you incorrect information, but I believe 60,000 digits. 60,000 digits. This person memorized pi, and this person is a savant. If you've ever heard of what a savant is, you can go Google it. So it's very interesting. They've been studying this guy to try and figure out how he thinks, because he doesn't memorize numbers the way we memorize. Like, not when I say we, I mean a majority of humans, the way we think of numbers. So here's the way he does it, to give you kind of an analogy. If I were to ask you to memorize 100 numbers in a row, that might be hard for you. It'd be hard for me. What he does is he says, think about like what you do every morning, right? Like, so like we all have kind of a routine, right? Like if you get out of bed, right? Assuming you sleep in a bed, you get out of bed, right? You can describe to me like everything in your room, right? Like you could tell me, oh, I've got a table there. It's got, you know, my charger for my phone on it. There's a clock. Oh, over there, I've got a little, you know, a flower, and up there is a TV. And then over there, I've got a little chair. And then I walk into the restroom and there's my toothbrush. And you can very vividly kind of recall everything around you, right? Does that make sense? Like if I asked you to really try and describe like the room you live in or something like that, you could do that, right? And you could probably come up with 100 things that you could say, oh yeah, I've got that drawer that has this and this and this and this in it, right? That's the way he thinks of numbers. It's like a scenery. And so the numbers are coming by him, and he's memorizing them because they have shapes and texture. It's really interesting. But okay, I'm going off topic. So E, at the end of the day, E is just the number 2.718. All right, about. Now, fortunately for us, our calculator has a key on it for E. All right, it has it. So I'll get to that in a moment, but I just want to go back. These two functions are the very special functions. This second one is called the natural exponential function. But please, just do not lose sight of this. This E is just the number about 2.718, all right? So these are two very special functions. I've told you they're special, but I haven't told you why they're special, right? I've just told you these are special. So let's talk about the base 10 one. Oh, by the way, are these gonna be doing the same thing in terms of growth and decay? Is one of them growth, one of them decay? Are they both growth? Are they both decay? What do we got?
Isn't base of 10 the growth, and then the natural exponential function, the decay?
Well, the
They're
base
both
here is
growth.
10, right? Is bigger than 1. So it's growth, right? So next, you're saying this right here, E is 2.718. That's also bigger than 1, right?
Yeah, so they both would be growth.
They're both growth. Now, which one grows faster?
Oh, the
Base
base of 10.
10.
Okay, I see.
Base 10, right? In order for it to be decay, right, you just need that number be less than 1, which neither of these are. So these are both examples of exponential growth. This one on the left grows faster than this one on the right, but they're both very special. So here, let's talk about why they're special. All right, so let's start with the base 10 one. Base 10 is actually, when we say base 10, I don't know if you've heard this before, but our number system is base 10. Have y'all heard that before? We use a base 10 number system. So what most of you don't realize, or like it's been so long since you talked about it, is that, go back and think about just the number 343, okay? Or let me do 345. We all understand what 345 is, right? If I said, hey, here's $345, like you understand what that number represents, right? But each of these digits, 3, 4, and 5, actually have meaning to them, right? This first 5, right, says you have 5 ones, right? This 4 tells you you have 4 tens. And the 3 tells you you have 3 hundreds. Right? So if I were to hand you 3 $100 bills, 4 $10 bills, and 5 $1 bills, that would be 345. So this is a very, very nice condensed way of writing all of this stuff together. Now, this is the crucial part. This is the same as 3 times 100 plus 4 times 10 plus 5 times 1, right? That's what this really means. Take 3 hundreds, add 4 tens, add 5 ones. Okay. Now, do you agree that this is the same as saying 3 times 10 squared plus 4 times 10 to the first power plus 5 times 10 to the 0 power? Think about that. Isn't 110 squared? Right? And isn't 10 10 to the first power? And isn't 1 10 to the 0 power? Yes? So notice that all of these are like little exponentials. 10 squared, 10 to the first, 10 to the 0, right? And these numbers just represent how many of those you have. So if I have the number 47601, right? This means I have 1 10 to the 0. Then I'm going to add to that no 10 to the 1s. And then I'm going to have 6 10 squareds. Then I'm going to have 7 10 cubes. And then I'm going to have 4 10 to the 4ths. Does that make sense to you? Don't worry, I'm not going to test you on this. I'm just trying to get you to see that our number system is based upon this 10 to powers, 10 raised to powers. All right. Why do you think we use base 10 number system? I mean, in our numbers, if I ask you to write a number down right now, you only have 10 options for digits, right? You can use 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the only digits that you can use to make up a number, right? Those numbers are made up of these digits. There's no other digits for you to use, right? So why do you think that we only have 10 digits in our number system? Or why do you think we decided to use 10 digits? Why not have 8 digits? Why not just have 5? Why not have 20? Why not have 23? Right? Why 10 digits? These are just symbols, aren't they? All they are symbols. I mean, I know we use them so much we don't look at them that way, but I could, if I want, have another, we could have had another number here, and it could have been this number. And maybe, I mean, you have no idea what that symbol is. I just made it up. But I mean, you could argue that the number 8 is just some crazy symbol, right? We're used to seeing it, but it's just a symbol. So why 10 symbols? Why 10 digits and not more or less? What do you think?
Is it so that way if scientists from different parts of the world communicate, they all are on agreement, like on a social agreement with what the numbers mean? So it's universal. That's what I'm trying to say.
Yeah, well, it is universal. We all use base 10. We do. But we could have all decided to use base 8. Like we could have said, hey, there's only these 8 digits. Or we could have said, hey, there's these 16 digits. Or, you know, whatever we wanted. Why 10? Why 10? It's unique to humans.
Because we have 10
Because we have
fingers.
10 fingers.
We have 10 fingers. If we had 8 fingers, we would most likely be in a base 8 number system. We would only have, we would then, like imagine we didn't have thumbs. Well, if we didn't have thumbs, we'd be in a worse position than we are right now. But if we only had 8 fingers, then the only digits you would probably ever have learned would be those 7. Now, we may have called them something else or, you know, but you would only have 0, 1, 2, 3, 4, 5, 6, 7. Those would be the only digits you've ever seen in your life. These other symbols, 8 and 9, would look completely foreign to you. Does that make sense to you? It's weird. It's because we have 10 fingers. So if someday down the road we ever discover there's other life out there, some alien life, I'm willing to bet everything I own that if they have fingers or anything like we do, if they have a different number, then their number system's probably going to be based on however many fingers they have. Because this is where we count, right? This is where we first learn to count, is on our hands. So that's why the base 10 exponential function is so important, is because our number system is base 10, and it's because we have 10 fingers, all right? So a very important function. And then this one is special for a reason that's very difficult to explain, but it's essential in a calculus class. So this is like, I'll try my best. What time is it? I'll try my best to explain this with a graph. Let me just do a new graph. So if I type in here e to the x, it graphs it for me, okay? So here's what's special about this graph. I have to do something real quick. 1 minus e raised to the m equals e to the m times x minus m. Okay, and then one more thing, m e to the m. All right, so there's the exponential function, right, in red. In calculus, we study functions and we look at something called the tangent line. So do y'all see this line that is running along this curve? You see how it kind of like just touches the curve at one point, kind of stays like in this weird sort of balance with the function. Y'all see that? Okay, that purple thing is a line, right? That's a line. So do you all agree that if this is a line, it has a slope? Like right there at this, let me move it a little bit, hold on. Move it over to the side. Come on, get there. It's not gonna, there we go. So do you all agree that this line has some slope to it, right? We don't know what it is, but it has a slope because all lines have slopes, right? Except vertical ones. Well, it turns out that this function e to the x has a very special property to it that if I wanted to know what this was, right? If I wanted to know what the slope of this line was, it will actually be equal to the height of this point, which is basically the y coordinate of this point. So if I move the graph, if I move that line somewhere else and I want to know how steep is that one, then all I have to do is go look at its y coordinate. If I want to know, how steep it is here, I just go look at the y coordinate. E to the x is the only function that exists that has that property. There is no other function. It is the one. And we are not quite sure why it is the one, but it is. And so it just kind of naturally occurs that this is like the function that behaves this way. So we call it the natural exponential function. Okay. All right. So Do you think you could graph these? Let's see. I think you could do this one. If I asked you to sketch this, I think you could, because you just make your little table, right? And then do your points. This one though, if I ask you to sketch it, we need to make sure we know how to use our calculator for this. So let's plug in some points. So on this calculator, okay, I'm again using the one you're supposed to have for this class. You'll see a key. Let me go to a new page. On your calculator, okay, you'll see a key on this left side. There's a key that says second. Below it, there's a key that says LOG, and then a key below that that says it's LN. That's not IN. It's not an IN. It's an LN, but they write it like this, okay? All right, do y'all see those keys on your calculator? Now the second key is green. Do you see that? And above that LN key, do you see written in green e to the x right above that key? What you're going to do is you're going to hit the second key. That turns everything to the green functions on here. And then you're going to hit the LN key. And when you do that on your screen, you should see the screen pop up with an E with a little box like that. And this should be flashing. And then you put in the number that you want to put in. So let's do E cubed first. Let's do e to the third power. And you should get 20.08 something. So if you do not have this calculator, that's fine, but please make sure you can get that answer. Does anybody have a question? Remember, you can't use a phone on a test. So,
Excuse me, how did you get the 20?
well, are you using this calculator or you have a different calculator?
Yeah, I'm using the same.
Did you hit the second button first?
Yes.
Then you hit the button that's 2 below that one?
Yes.
And did it pop up with a little E with a little box?
Yes.
And did you put 3 in there?
Okay, yeah, got it.
Got it? Okay. So if we plug in 3, we get 20.08. Let me just do these. If I do e to the second power, 7.39, e to the first power, 2.718, e to the 0 is 1, e to the -1 is 0.36, e to the -2 is 0.135, and then e to the -3 is 0.049, something like that. Please be sure you can get those. All right. Any questions on that? So if I graph this, I just need to make sure that my y goes up to at least like 20. Maybe I go to 25. I don't know, but it's kind of up to you. Okay. We good? All right, we're moving on. We're now going to really switch gears. All right. We're not going to talk about graphs anymore. We're going to talk about where we would see an exponential function in the real world. All right. So there is a thing called simple interest. All right, so simple interest is the idea that if you go and put money into a bank, right, then the bank is going to give you money for allowing them to hold on to your money. So like if you have, here's a bank, here's the bank, right? And here you are. And you decide to take your money and put it into the bank. The bank says, okay, thank you very much. Every month, we're going to give you a little bit of money for letting us have your money. And the way they calculate that is by using a formula, and it's called a simple interest formula. Isn't that nice? The bank pays you to hold on to your money. Isn't that nice? They don't pay you much though, okay? It's insignificant. I mean, it's so low, okay? It's so low what they pay you. It's ridiculous. It used to be a lot higher. So how does the bank stay in business if that's what they are, if they're paying you to hold on to your money? How do they make money? How does a bank actually make money then?
They're loaning out the money and they make money off of the interest from those loans, and the money that they're using for the loans is technically your money, which is why
That's
you get
right.
interest.
Exactly. So you've got people who have money, they put their money in the bank, right? And then you got these people over here that are like they've got big eyes and they've got like this straight look on their face, like, I need money, right? So they take money out. Now, when I say they take money out, that's usually in the form of a credit card, or they take a loan on a car, or they take a loan on a house, right? So these people take money from the bank. Well, guess whose money they're borrowing? It's actually this person's money. It's not the bank's money, okay? The bank is basically a middleman. The bank is borrowing your money, giving you a little bit money, and then giving that money to somebody else and making them pay that back every month with this huge interest rate. So it's like, if you borrow $1,000, right? You borrow $1,000, you might have to pay back to them maybe $1,300 because of interest. Credit cards have huge interest rates. Now, these people, maybe they put in $1,000, and then the bank is going to give them a little bit of money. So if they pull their money out, then maybe it's $1,005. So they make $5 off their money, So the bank is going to collect the difference, right? They made $300 off of this person, and they had to give $5 back to this person. So they made $250. Does that make sense? I mean, that's the way it works. So what happens if everybody, right? What happens if everybody over here all shows up at the bank one day and says, give us our money?
They ain't got the money.
They ain't got the money. Okay, they won't have the money. And so you run into a major problem, which is why banks have what's called the FDIC, federally insured. So basically the federal government has said, look, if everybody comes knocking one day and wants their money, if a bank is federally insured, they will say each one of you is guaranteed to get your money, guaranteed. The government will come in and give you the money themselves, but up to a limit. They'll only insure up to $100,000. That's it. So if you have $400,000 in here and you come knocking for it one day, hey, I want my $400,000. If the bank can't get it to you, then the most you're going to get back out is $100,000. That's what you'll be guaranteed. So that's why you never put all your money into one place or whatever. Okay, so this was all just to give you some idea of how banks work. I mean, this is a very general kind of idea, right? It's more complicated than this, but generally speaking, this is the way it works. So the formula that we use to figure out how much money, it works both ways. To figure out how much this person's going to owe back and to figure out how much this person's going to get back, that formula is a simple interest formula, and here it is. And when I write it, you're going to be maybe surprised to see something in here. It is A equals P E raised to the R times T. All right, so there's a ton of letters in here. Let me explain what each letter is, all right? So P in this is what we call the principal. This is the starting amount. So if you're the person putting money into the bank, this would be the $1,000. If you're the person borrowing money from the bank, this would be the money you borrowed to start with, okay? The next important thing here is T, and this is time, and it's measured in years. So if this person goes and puts $1,000 into the bank and says, hey, I'm going to leave that in there for 2 years, then T would be 2. Understand? What would T be if they decided to leave their money in there for 6 months?
0.5.
0.5, half a year, right? So you have to be a little careful because 6 months is half a year. So you would use 0.5 for T. All right, so that's what P is. P is the amount of money we start with. T is the time we're going to have that money, or in this case, the amount of time that this person is going to borrow the money. R is the critical number here. R is what's called the interest rate. Okay, it's normally given as a percentage, but in the problem, or in the formula, it must be a decimal. Interest rates are the most important parts of any borrowing money, or anytime you put money into a bank and want to know how much you're going to get back from the bank, or if you borrow from the bank, take a credit card, the interest rate's the most important number. Because I mean, like, if I told you right now that I'll loan you $100, but you have to pay me $150 back, that means you're paying me $50 to borrow 100, right? That's a lot of money to pay to borrow $100. But if I say, hey, I'm going to loan you $100, you only have to pay me back $101 back. Well, then you only paid $1 to borrow $100, right? That's better. That's a lower interest rate. So the smaller the number the smaller that this is, the better for you if you're borrowing money. That makes sense? The smaller the interest rate, the better for you if you're borrowing money. Does anyone know what like credit card interest rates are?
Isn't it like 20 something percent?
Yeah, I mean, I've seen credit cards. I don't think I've seen under 10% in the last few years, but I know they get into the 20s. That is a huge, huge interest rate. That's basically like saying for every $100 you borrow, you're gonna have to pay back about $25 back. And if you don't pay it back, it's gonna add on top of itself and you're gonna keep owing more and more. Credit cards are so dangerous because of the high interest rates. Do y'all know right now that if you were to try and buy a house, that the interest rates are at an all-time low? Do you have any idea how much the interest rates are about? It's about, what do you say?
4.
Yeah, I haven't looked lately, but it's between 2 and 4. Okay, that's a low rate. That's a low rate. There was a time where it was up at like 8%. If you look at, I like to go to, let's see, is it Fannie Mae? Fannie Mae interest rates. It's on my search history. We were thinking about, let me see if I can find. Well, mortgage rates are climbing. So here are the rates. Look at the blue one. You can see it's gone up. I want to look at I want to look at all time. This is going back to 1971. So back in, let's see, back in the 80s, if you wanted to borrow money to buy a house, your interest rate was 17%. That is crazy. And then it's gone down, gone down, gone down. And we've reached this point recently where they're down at like 2%. That is extremely low. Extremely, extremely low. It's like every $100 you borrow, you're going to owe 102 back, roughly. So that's good, that's good. It's more complicated than that, but it's all-time record lows, right? I All right, so get back to the formula. So the R is the interest rate. What do we still have in the formula? A. Okay, so what is A? A is the amount at the end of time. So the left side of this equation is going to tell you how much you'll have after a certain amount of time. So like, for example, if I take money and I put it into the bank and I leave it in there for a while, let's say I leave it in there for 2 years, and I come back and I say, okay, after 2 years, I want my money back. The A will tell me how much money I'll have, all right? The only other thing in the problem that I haven't accounted for is the E, but E is that special number. That's that 2.718. So we're never going to need to replace E with anything. All right, so let's just do an example. Let's see how this works. Let's say you put $5,000 into an account for 3 years at 2.3% interest. How much is there after the 3 years? All right, so let's see. Let's use the formula, right? A equals P E to the RT. I call this the shampoo formula. Have y'all ever heard of PERT before? PERT, the shampoo? No?
I haven't heard of the shampoo, but I remember calling it this for this formula was a pert. We just called it
A-PERT?
that.
Yeah, a PERT. It's a shampoo. So
Shampoo.
what there it is. PERT. It's good stuff. I use it because it's formula, so I have to have it in my house. PERT. What's A? We have to figure out what everything is here, right? So what's P for us? Do we know P? Do we know how much we started with?
5,000.
5,000. Okay, so that's 5,000. All right. Do we know R? Do we know the interest rate? Or T?
2.3%.
2.3%. But I said in the formula, it must be a decimal. So how do we convert a percentage to a decimal? This is important. If you don't know how, this pay
Move
attention.
it
You move the decimal which way?
left.
Left 2 places. So if you move that decimal 2 places to the left, put it here, you're going to get 0.023. Do we know T, the time that we're leaving it in there?
3
3, right? Because
years.
3 years, so we will just put 3 there. And that's it. Those are the only pieces we need. Now to figure out the amount, we replace everything. So P was 5,000. E raised to the 0.023 times 3. Make sure you understand that we're going to be taking that R, whatever R is, and multiplying it times the T, which is the 3. So again, for those of you who have this calculator, I'd like for you to see if you can type this in all at the same time. So you'll start out by typing in, 5,000, then hit times, and then bring up that little E. that we had earlier, E, it's going to give you a little box here. In the box, put your 0.023 times 3. And then after you've typed that all in, you should be able to hit enter. Y'all can't see that, can you? That's what I've got there. Anyone have an answer?
5,357.18.
0.18. That's what you should get. So you have more money now than you put in, right? You could figure out how much more, right? By just taking the amount here and subtracting that, and that would be how much you earned, right? That'd be how much money you earned. So if I took the 5,357.18 and I subtract the original amount, 5,000, it would come out to 357.18. That's how much the bank paid me to hold on to my money for 3 years. It's a little over $100 a year is what they paid me. Make sense? Okay, so we're almost out of time. I'm going to give you your homework assignment, all right? What I'd like for you to do for homework is I want you to sketch the following. F of x, and this is just for practice, okay? F of x equals, let's do 0.125 to the x. The next one I'd like you to do is, let's go ahead and do that 10 to the x, the base 10, because the numbers are going to get real big here. I just want to kind of see what your graph looks like. And then the third problem I'd like for you to do is basically, I'm going to have you do 2 of these word problems right here. I'm just going to copy this and write some new ones here. So let's say for the first one, I'm going to change some things around here. Let's say that you do, instead of $5,000, let's say that, let's say you win the lottery. Okay, not a huge one, just a minor one, I guess. Let's say you win $1 million. Okay, $1 million. So you decide to put that, you're not quite sure what you want to do with it. So you put it into this account and you leave it in there for just a year. You decide, you know what, I'm not going to go crazy with this money. I'm just put it in the bank for a year. And let's say that the interest rate here is, boy, let me see what the highest rate that I can find. Bank CD rate 1 year. It's going to be so low. Let me see. 0.75. I'm just going to go off the first thing I see there. Bank rate 0.75 looks like the best I'm finding. That's a very low rate. So the interest rate is 0.75%. Be careful. It's a decimal, right? But it's a percent. It's a percent. It's a decimal of a percent. So you still need to convert that to a decimal. And how much is there after 1 year? 1 year. Understand the question? All right. For the fourth one, here's what I want you to do. You borrow $2,500. Basically credit card, all right? You go make a purchase on a credit card. Now, you're supposed to pay back every month, right? Or else they get mad at you. But let's say that you don't pay it back, okay? And you borrow it, and then for 2 years, you don't make any payments. And the interest rate, let's say, is 16.25%. How much do you owe after 2 years? Now I realize they would already have come after you and you have all these penalties and late fees and all that. Let's just ignore that. Let's just say that you borrowed $2,500, made a credit card purchase. You don't pay any of it back for 2 years, but the interest rate is 16.25%. After 2 years, how much are you going to owe? Understand these questions? Both of these, you're going to use the shampoo formula. These you're just going to graph using the table. Okay, I'm sorry I went over on time. Y'all have a great weekend. Be looking for the review in the next 24 hours, okay? Have a great day, everyone.
Thank you.
Good weekend.
Bye.
Thank you.